Hello everyone, hope you all are doing good. I am Anjana from LearnoHub, the free learning platform where you can study math, science and SST absolutely free at learnohub.com. In today's class, we are going to discuss ICSE Class 10 Physics Chapter 4 Refraction of Light at Plane Surfaces. We will be discussing what refraction is and the refraction through a rectangular glass slab. We will also be solving problems that are related to it. What is refraction? Just look at this figure. This is an experiment that you can perform. Take a glass of water and put a pencil like this. Okay. When you look at this from outside, you will be seeing that there is a bending happening to the pencil. Does it really happen? No, right? The pencil will be straight. But when you look it from outside, you will be seeing a bend. And the reason for this is refraction. Okay. Now, what is refraction? We have studied in detail about reflection in class 9th. When you have a smooth surface, a plane mirror, and when light ray falls on this, what happens to this light ray? This light ray touches the surface and bounces back. Okay. Then you will be having angle of incidence and angle of reflection. We have studied the laws of reflection, incident ray, reflected ray, normal. At the point of incidence, all lie on the same plane. And the second law was angle of incidence is equal to angle of reflection. Now, what is this refraction? When we have two mediums, okay, when light is traveling from one medium to other, what happens to the light is, the light path will change. The direction of light will change, okay. A part of this will be getting partially reflected and a part will be refracted to the new medium. It will be going into the new medium. Okay, so this process of bending of light when light travels from one medium to other is called refraction. The change in the direction of path of light when it passes from one transparent medium to another transparent medium is called refraction. So, got the basic idea what refraction is? In case of refraction, this is your incident ray. Okay. Here partial reflection is happening. So, this is reflected ray. In this chapter, you won't be considering this reflected ray. You can just neglect this. And this is your refracted ray. Here you have the normal. We have studied about normal when we studied about reflection. Normal is a straight line which is perpendicular to the surface. Okay. Which is at 90 degree. The angle between the normal and the incident ray is angle of incidence. Angle between the normal and the refracted ray is angle of refraction. Got the basic idea? So, this is what a process of refraction is. We will be considering two cases, that is when light travels from a rarer medium to denser medium, and the second when light travels from a denser medium to rarer medium. For example, if we take air and water. Air is a rarer medium and water is a denser medium. Density is more for water. So, here the first cases we are considering light traveling from a rarer medium to denser medium. We know that light will always be in a straight line path. Okay. Light has rectilinear motion. Light travels in a straight line motion. But when light travels from one medium to another, that is in case when light travels in vacuum or in air in a single medium. But when light travels from one medium to another, we will not be considering the reflection, the partial reflection. We are considering only the refraction. Light is bending. Okay. Here you can see the light bending. This is the actual path of light. Here we have the incident ray. Okay. This is the actual path of light. What is happening to light here when it moves from rarer to denser medium? For example, air to water. What has happened? The light ray has bent towards the normal. Now, what is this normal? We know, right? It is a perpendicular drawn to the surface. Angle will be 90 degree. Okay. Now, the angle between, this is your incident ray, angle between incident ray and normal is taken as I, angle of incidence. Similarly, you have angle of refraction. Here we have angle of refraction, the angle between refracted ray and the normal. Now, this is the deviation that has happened from the actual path of light. What has happened? There is a shift. Okay, there is a shift in the refracted ray. So, this angle we will be representing as delta. angle of deviation it is, how much it has been shifted from its actual path. Okay, now when you consider this normal and the path of light, original path of light, you can see that these two lines cut at this point, then you will be having vertically opposite angles. Okay, you can have I is equal to R plus delta. Incident angle is equal to angle of refraction plus this angle of deviation. From this you will be having angle of deviation is equal to angle of incidence minus angle of refraction. Clear? So when light travels from air to water, it bends towards the normal. Or when light travels from a rarer medium to a denser medium, when a ray of light travels from a rarer medium to a denser medium, that is air to glass, it bends towards the normal. Okay, now the second case. Here you have the second case. Denser to rarer medium. With our example, water to air. Denser to rarer medium. What is happening in this case? You have the incident ray, normal, angle of incidence. Okay. Now this is the normal and this is your angle of refraction. Here you have the refracted ray. From the actual path, it is moving away from the normal by an angle delta. This is your angle of deviation. Okay, now how to find angle of deviation? Here, this is angle of incidence. Here we have angle of refraction and this is angle of deviation. Now, when you consider these two lines, that is actual path of light and the normal, vertically opposite angles will be I and this part. What is this part? This part will be total angle of refraction minus the shift, angle of deviation. Okay, so you will be having I is equal to R minus delta. Then what is delta? Taking this delta to the opposite side, delta is equal to R minus I. Okay, so angle of deviation in this case, that is when light travels from denser to rarer medium, you can determine like this: refractive angle minus angle of incidence. In case when light travels from rarer to denser medium, the angle of deviation will be angle of incidence minus angle of refraction. Okay, so we can conclude that when a ray of light travels from a denser medium to a rarer medium, glass to air, it bends away from the normal. First case, it bends towards the normal. Second case, it bends away from the normal. Understood? Now, if you are taking, here we have taken the example of air and water. If you are taking water and glass, rarer medium is water and glass is your denser medium. When light travels from water to glass, it bends. The light ray will be bending towards normal. It bends towards normal. Okay. Now, this the opposite, that is glass to water. Light is traveling from glass to water. In that case, it bends away from the normal. Away from normal. Okay. Now, the third case is refraction at normal incidence. What does normal incidence mean? Here you have a surface S dash. Now, AB is your normal or AB is your incident ray. Here you can see this is your incident ray. Incident ray coincides with the normal. Normal will be at angle 90 degree with the surface S dash. First medium, second medium. Air is taken as the first medium, which is a rarer medium, and glass or water can be taken as the denser medium, second medium. Okay. Here you have the incident ray and this is your refracted ray. Now, what is the angle between the incident ray and normal? Angle of incidence. In this case, what is angle of incidence? Angle of incidence is equal to 0 degrees. Why? Because normal and the incident ray are coinciding. Similarly, what is the angle of refraction? Angle of refraction is also equal to 0 degree. Why? Because normal and the refracted ray are also coincide. Even though the light travels from one medium to another medium, the light will be following a straight line path. It won't be deviated when it is at normal incidence. Okay? Incident ray coincides with the normal. So that we can say the ray of light incident normally on the surface separating the two media passes undeviated. Okay, there is no deviation. Angle of deviation will be equal to 0 in this case. Now, what causes refraction? We said when light travels from rarer to denser medium, it bends towards the normal. When it travels from denser to rarer medium, it bends away from the normal. What is actually happening? When a ray of light passes from one medium to another medium, its direction or path changes because of change in speed. This is important. There is a change in speed of light. In air, we know that light travels with a speed c is equal to 3 into 10 raised to 8 meter per second. Okay, when the light travels from this air to another medium like water or glass, what is happening is there is a change in the speed of light. First case, rarer to denser medium. What is happening? The light will start to slow down. Light which was traveling at a speed 3 into 10 raised to 8 meter per second. Here, this is your surface. You have normal. This is your incident ray. And this incident ray in air medium is traveling at a speed 3 into 10 raised to 8 meter per second. Okay, when it touches the surface, here you have a denser medium. Let us take the case of water. The speed of light is going to decrease. Okay, speed of light will decrease. In that case, we know it will bend towards the normal. And this is your first case. Light slows down. Rarer to denser medium. Okay, light slows down. When light slows down, what is happening? The light bends towards the normal. Now, just the opposite case. That is denser to rarer medium. When light travels from a denser medium to a rarer medium. Here, the air we are taking in the second part. That is second medium is air. Air is your second medium. This is your light ray. It will bend away from the normal. Now, what is happening? The speed of light is increasing. Okay. When light ray travels from denser to a rarer medium, speed of light is increasing. In that case, it will bend away from the normal. Light bends away from the normal. Second case. Now, even though if the speed of light remains the same, there may be no change in direction. Okay. That is the case of normal incidence. In normal incidence, sometimes there may be speed of light change, but the direction will be the same. This is how the light will go. Okay. In that case, that is when speed of light will remain the same, in that case, there is no bend in light. Light does not bend. Clear? Now we will be discussing the laws of refraction. When we studied about reflection, we studied two important laws. The first law was the incident ray, the reflected ray and the normal at the point of incidence lie on the same plane. Here again we have a similar law. The first law is the incident ray, the refracted ray and the normal at the point of incidence all lie in the same plane. Only difference is in place of reflected ray, you will have to change it to refracted ray. Okay, so this is your first law. Second law, what was the second law of reflection? It was related to two angles, the angle of incidence and the angle of reflection. What was it? Angle of incidence is equal to angle of reflection. Now here we have to take the ratio of sine of angle of incidence and the sine of angle of refraction. Angle of incidence, angle of refraction, we will be taking the ratio of their sine. Okay. In that case, when you take the ratio of their sine, you will be getting a constant value. And this constant will be representing by mu. This is your second law. These two laws are known as Snell's laws of refraction. Okay. Snell's laws of refraction. This is the first statement. First is similar to the first law of reflection. And the second is a law which gives a relation between angle of incidence and angle of refraction. There you had angle of incidence and angle of reflection. Here it is angle of incidence and angle of refraction. When you take the ratio of their sines, you will be getting a constant value and this constant value is represented by mu. Okay. What is mu? Mu is known as refractive index. Mu is known as refractive index. The sine of angle of incidence to the sine of angle of refraction is equal to a constant which is refractive index. We will study this in detail. Now we have the refractive index. Consider a surface. This is the normal incident ray. Here you have the incident ray and we are considering two mediums. Medium 1, let us take the first medium as air. And this is your second medium. Medium 2. Let it be glass. Now what happens to the ray of light? It bends towards the normal because we are traveling, the light is traveling from rarer medium to a denser medium. This is your angle of incidence, the angle between incident ray and normal. This is your angle of refraction. Okay. Now, when you take the sine of angle of incidence and the sine of angle of refraction ratio, you will be getting a constant value. This will be a constant. And this is equal to mu. As we said before, mu is the refractive index. Refractive index of the second medium with respect to first medium. This is how you represent it. Okay. Either you can write mu21 like this or mu21. Both are correct. Okay. Refractive index of the second medium with respect to first medium. Clear? So, sine of angle of incidence to the sine of angle of refraction ratio is a constant, which is a refractive index. The refractive index of second medium with respect to the first medium is defined as the ratio of sine of angle of incidence in the first medium to the sine of angle of refraction in the second medium. This is how you can define refractive index. Next is the effect on speed, frequency and wavelength due to refraction of light. When refraction of light takes place, what is happening to speed, frequency and wavelength of light? The first point is related to the speed or velocity of light. When a ray of light gets refracted from a rarer to denser medium, we have studied this. Rarer medium to denser medium, when a ray of light travels, its velocity will decrease. Okay, speed of light will decrease. When it travels from a denser to a rarer medium, its velocity will increase. Okay, here the refraction is increasing and in this case the refraction is decreasing. Velocity increases, refraction decreases. Now the second is related to frequency. The frequency of light depends on the source of light, so it does not change on refraction. It is only dependent on the source of light. For a given set of medium, the frequency will be same. Frequency of light is a constant and it doesn't change for a given source of light. Okay, frequency is a constant. And the third is the speed of light V in a medium is related to its wavelength lambda, and the relation is V is equal to F lambda. If the first medium is air, then we will be having C is equal to F lambda, from which we can write lambda is equal to V by F. Okay, frequency we know is a constant, which means lambda is directly proportional to velocity. When velocity increases means denser medium to rarer medium, velocity increases, lambda also increases. Okay, when velocity decreases, lambda also decreases. When you have VIBGYOR, which color has the highest wavelength? Highest wavelength is for red light. Okay, maximum lambda, and violet has minimum lambda. Okay, maximum wavelength means speed of light is maximum. Then in that case, refraction will be minimum. Minimum wavelength means speed of light will be less, which means refraction is maximum. Okay, so when wavelength increases, refraction will decrease. Clear? So this is what is absolute refractive index? The relationship between refractive index and speed of light. We know that speed of light is different in different medium, and the maximum speed of light is when light travels in vacuum or in air. The speed of light is maximum in vacuum, and that is equal to 3 into 10 raised to 8 meter per second. All other velocity of light in different mediums will be less than 3 into 10 raised to 8 meter per second. Okay. Now we can define refractive index as the ratio of speed of light in vacuum or air to speed of light in that medium. This is what absolute refractive index is. When you don't consider air as the first medium, any two mediums you are considering, we just call it refractive index. But it is absolute refractive index when light is traveling from air to any medium. Either it can be air to glass or air to water. In all these cases, we will be having absolute refractive index because the first medium is air. Light is traveling from air to any medium. Okay. So when it is from air to glass, we represent as mu g. Okay. Which means the refractive index of glass with respect to air. Or to find the value, how can you take? We'll be having the speed of light in vacuum or air, that is C, and we have to find the speed of light in glass when it is traveling from air to glass. So let it be Vg. Vg is the velocity of light in glass. So mu g will be equal to C by Vg. If it is traveling from air to water, in that case, let us represent it as mu W. That is refractive index of water with respect to air. And that will be equal to speed of light in air or vacuum divided by the speed of light in water. Okay. Now we know that maximum speed of light is in vacuum. Yes, that is 3 into 10 raised to 8 meter per second. So when you will be having a value less than 3 into 10 raised to 8 meter per second in the denominator, anyway, Vg will be less than C. Also Vw will be less than C. Why is it so? Because we know that maximum velocity is when light travels in air or vacuum. Therefore, the velocity of light in glass should be less than the velocity of light in air. Velocity of light in water should be less than the velocity of light in air. In that case, that is when denominator is less than the numerator, what will be the ratio? Is it greater than 1 or less than 1? The ratio will surely be greater than 1, right? The value will be greater than 1. Which means the refractive index of glass or the refractive index of water will have a value which is greater than 1. Just remember this, the ratio will be greater than 1. For example, that is we can say that the absolute refractive index or refractive index of any medium will always be greater than 1. Why? Because the velocity of light in any medium will be less than the speed of light in air or vacuum. Okay. Refractive index value will always be greater than 1. Let us take some examples to find refractive index. The speed of light in air is 3 into 10 raised to 8 meter per second. C is given. C is equal to 3 into 10 raised to 8 meter per second. And in glass it is 2 into 10 raised to 8 meter per second. Velocity of light in glass is equal to 2 into 10 raised to 8 meter per second. What is the refractive index of glass? We have to find the refractive index of glass. Refractive index of glass mu g is equal to C by Vg, which is 3 into 10 raised to 8 meter per second divided by 2 into 10 raised to 8 meter per second. 10 raised to 8, 10 raised to 8 can be cancelled. 3 by 2. That's 1.5. Okay. Now the second part, the speed of light in water is given. Vw is equal to 2.25 into 10 raised to 8 meter per second. We know what C is. Speed of light in air is 3 into 10 raised to 8 meter per second. We need to find the refractive index of water. Refractive index of water, mu W is equal to C divided by Vw. That is 3 into 10 raised to 8 meter per second divided by 2.25 into 10 raised to 8 meter per second. When you calculate this, you will be getting a value 1.33. Now check all these values, 1.5, 1.33. These values are greater than 1. Okay. It is getting greater than 1. Since refractive index is a ratio, there is no unit for refractive index. There is no unit. It is a ratio. Here you can see that meter per second will get cancelled. Numerator and denominator, when you have the same units, they gets cancelled. Therefore, refractive index has no unit. Next is relative refractive index. We understood what absolute refractive index is. In case of absolute refractive index, the first medium will be air. Relative refractive index is when there are two mediums taken. It is not necessary that the medium should be air. One medium should be air. You are considering the light traveling from first medium to second medium. Okay. We know that refractive index is ratio of the speed of light in first medium to the speed of light in second medium. Speed of light in medium 1 to the speed of light in medium 2. Or it can be represented by mu 2 1. It can also be written as mu 2 1. The refractive index of second medium with respect to the first medium. Speed of light in first medium by speed of light in second medium. We know that absolute refractive index. The absolute refractive index of first medium will be C divided by V1 and absolute refractive index of second medium will be equal to C divided by V2. where V1 and V2 are the speed of light in the two mediums. Okay, from this we can write V1 is equal to C by mu1. From this we can write V2 is equal to C by mu2, just crossing. Okay, C by mu1 and C by mu2. Now we have mu21 is equal to V1 by V2 will be equal to V1. V1 is C divided by mu1 divided by V2. V2 is C by mu2. Taking the reciprocal, C by mu1 into mu2 divided by C. Just taking the reciprocal of this denominator part. Then C gets cancelled. You will be getting mu2 by mu1. Therefore, the refractive index of second medium with respect to the first medium is refractive index of the second medium divided by the refractive index of first medium. Let's take an example. Light is traveling from water to glass. Okay, speed of light in water VW is equal to 2.25 into 10 raised to 8 meter per second, and speed of light in glass is equal to 2 into 10 raised to 8 meter per second. Okay, 2 into 10 raised to 8 meter per second is the speed of light in glass, and speed of light in water is 2.25 into 10 raised to 8 meter per second. Now, if we need to find the refractive index of glass with respect to water. Why? Because water is the first medium and glass is your second medium. Okay, will be equal to, we can write this as velocity of light in water divided by velocity of light in glass. Okay, that is equal to 2.25 into 10 raised to 8 divided by 2 into 10 raised to 8. When you take the ratio, you will be getting 1.125. Okay, 1.125 is the refractive index of glass with respect to water. Now just the opposite. When light is traveling from glass to water, we know the values. We'll be finding the refractive index of water with respect to glass, or mu Wg. This will be equal to velocity of light in glass divided by velocity of light in water. What is the velocity of light in glass? That is equal to 2 into 10 raised to 8 divided by, in water it is 2.25 into 10 raised to 8. 2 divided by 2.25, you will be getting a value 0.89. Okay. This is the refractive index of water with respect to glass. They both are different. Okay. Refractive index of glass with respect to water and the refractive index of water with respect to glass, you will be getting two different values. Remember this point. Now we will be studying the two conditions for a ray to pass undeviated on refraction. Undeviated means in a normal incidence case. So here you have the surface. This is your incident ray. This is your refracted ray. So when the angle of incident at the boundary of two medium is 0. We know that the normal incidence case, here you are having the incident ray. This is the same as your normal. Therefore, angle of incidence will be equal to 0. If angle of incidence between the two medium is equal to, between the boundary of two medium is equal to 0, the ray of light will be undeviated. It will be going along the same straight line path. First one. Second, when the refractive index of medium 2 is same as that of medium 1. We know that refractive index, relative refractive index is represented by mu21. What is mu21? Mu21 is mu2 divided by mu1. Okay. When the refractive indexes is same, you will be getting the ratio to be equal to 1. We know that according to Snell's law, sin I by sin R is equal to mu21. Refractive index of the second medium with respect to first medium. I is the angle of incidence and R is the angle of refraction. Sin I by sin R will be equal to mu21. Okay. Now when this mu21, when mu1 and mu2 are equal, in that case this value will be 1. Which means the ratio of sin I by sin R is equal to 1. What does it mean? Sin I will be equal to sin R. If sin I is equal to sin R, then angle of incidence should be equal to angle of refraction. So, two cases when incident angle is equal to 0 and refracted angle equal to 0. In that case, you will be getting the ray to pass undeviated. And the second is when the angle of incidence is equal to angle of refraction. That is mu2 1. Both the mediums are the same mediums. Okay. Medium 1 and medium 2 are same. If medium 1 and medium 2 are same, their refractive indexes will be same, then angle of incidence will be equal to angle of refraction. In that case also, the ray will go undeviated. Relationship between wavelengths in the two different mediums. Okay, here we have two mediums. Let's say air and water. This is your first medium. Let's represent it by mu1. And this is mu2 of refractive index mu1 and mu2. First medium of refractive index mu1, second medium of refractive index mu2. Now we are considering a ray of light of wavelength lambda and frequency f. Okay, so here you have to remember one point, frequency is never going to change. When light ray travels from one medium to other, wavelength can change but frequency will always remain c. Now what about velocity of light? Velocity of light will also be different. Okay, in different medium, velocity of light is different. In air, we will be having velocity of light to be equal to c. Okay, and in water, let's say the velocity is taken as v. Okay, now we can write a relation, that is, we have velocity is equal to wavelength into frequency. So first, in the case of air, first medium is air. In case of air, we will be having c is equal to lambda f, from which the frequency f is c by lambda. Okay. Now the light ray travels from this medium to the second medium. Light travels from air to water, rarer to denser medium. What happens is the velocity is changing. With this, the wavelength is also changing. Let's say now the wavelength is lambda dash. Here velocity v, velocity of light in water, v is equal to lambda dash. Frequency is the same, we can represent it by f. Okay, which means here we will be having frequency f is equal to v divided by lambda dash. Okay, so this is your first equation and this is your second equation. When you check these two equations, you can find the left hand side is frequency, left hand side is f. Okay, therefore right hand side should also be equal. C by lambda will be equal to v by lambda dash. Cross multiplying, we get c lambda dash is equal to v lambda, and then lambda dash is equal to v lambda divided by c. What does this mean? You can find the wavelength of light in the second medium by knowing the wavelength in the first medium, velocity of light in the second medium and the velocity of light in first medium. Here the first medium is air. Okay, we have a relation, refractive index mu is equal to velocity of light in air divided by velocity of light in a given medium. Okay, here velocity of light in air divided by velocity of light in water. Okay, for example, if mu2 represents the refractive index of second medium with respect to first medium, we can write this is equal to mu2 divided by mu1. Okay, now check this. Here we have lambda dash is equal to v by c into lambda. Okay, we have c by v is equal to refractive index mu, which means we can take the reciprocal of this. 1 by mu will be equal to v by c, taking reciprocal of the left hand side and right hand side. Okay, now substituting here, we get lambda dash to be equal to lambda divided by refractive index of the medium. Okay, now consider this case. If the light is moving from a rarer medium to a denser medium, which means the refractive index of first medium is less than the refractive index of second medium. Okay, second medium is denser. In that case, you will be getting the refractive index to be greater than 1. Yes, refractive index will be greater than 1. Why? Because numerator is greater than denominator. Okay, if refractive index is greater than 1, what does it mean? Here, this value, mu value will be greater than 1. So, when you divide wavelength with a value which is greater than 1, we will be getting lambda dash such that lambda dash is less than lambda, because we are dividing with a number which is greater than 1. Okay. Now, if the refractive index of the first medium is greater than the refractive index of second medium, which means the denominator is greater. Okay, if denominator is greater, then you will be getting refractive index to be a value which is less than 1. Okay, so if you are dividing wavelength with a value which is less than 1, then lambda dash will be greater than lambda. Understood? If the refractive index mu is greater than 1, then lambda dash is less than lambda. And if refractive index mu is less than 1, then lambda dash is greater than lambda. What does it mean? When refractive index mu increases, wavelength decreases. Okay. Here, rarer to denser medium. Light is traveling from rarer to denser medium, which means the refractive index is increasing. What happens to wavelength? Wavelength is decreasing for a given frequency of light. Okay. Next, the factors on which the refractive index depends. The first one is nature of medium. That is velocity of light. We know that when light travels from one medium to another, the velocity of light is changing, right? For example, the velocity of light in glass is equal to 2 into 10 raised to 8 meter per second. Velocity of light in water is equal to 2.25 into 10 raised to 8 meter per second. What about refractive index? We have determined that refractive index in case of glass is equal to, what is the value that we are obtaining? We will be getting 1.5. 1.5 is the refractive index of glass. And the refractive index of water is equal to 1.3. So when you check this, you will understand velocity of light in glass is less than velocity of light in water. What about refractive index? Refractive index of glass is greater than refractive index of water, which means the velocity and refractive index are inversely proportional. When velocity increases, refractive index decreases, and when refractive index increases, velocity decreases. Clear? Second is physical conditions such as temperature. What happens when temperature increases? In case of air, we have studied that hot air is less denser. Okay, hot air is rarer compared to normal air. So, when temperature changes, what is happening? We said hot air, when temperature increases, what is happening to density? Density is decreasing. Density is decreasing when temperature increases. Okay, density decreases means what about refractive index? Refractive index is also decreasing. Therefore, temperature is inversely proportional to refractive index. Second condition. And the third condition is the color or wavelength of light. How does wavelength depends on the refractive index? When you take VIBGYOR, maximum wavelength is for red light. Okay, minimum is for violet. Minimum wavelength is for violet light. Okay, refractive index, we know refractive index mu21 is mu2 divided by mu1, which is equal to V1 by V2 is equal to lambda 1 by lambda 2. Frequency is a constant. Okay, therefore what will be the dependence of wavelength and refractive index? The medium, that is for violet light, there will be having maximum mu value. Why? Because refractive index is inversely proportional to wavelength. Wavelength and velocity are directly proportional. Therefore, refractive index is inversely proportional to velocity and refractive index is inversely proportional to wavelength. And red light will be having minimum refractive index. So here when you take these colors, the wavelength is increasing. Wavelength of light is increasing from violet to red. What about refractive index? Refractive index will be decreasing and the minimum refractive index is obtained for red light. Principle of reversibility of the path of light. Now consider, here you have the surface. This is your incident ray, normal, and this is your refracted ray. Light is traveling from a rarer medium to a denser medium. Okay. This is the path of light. Now according to this principle of reversibility, it states that the light will follow exactly the same path if its direction of travel is reversed. What does direction of travel reversing mean? Here, if this light is traveling from the opposite mediums, that is, light is starting from here and traveling to this new medium. Okay. Rarer to denser medium is the first case. Then this is your path of light and Denser to rarer medium if the light is traveling. The light is starting from here. If this is your incident ray, then the refracted ray will be the same. Okay, for a given set of medium. This is your rarer medium and this is your denser medium. Okay, so this is how it is. You will be having, in case of air and glass, the refractive index of glass with respect to air, because light is traveling from air to glass. The first medium is air and second medium is glass. Okay, mu Ga, that will be equal to mu G divided by mu A. Yes, and this is sin I divided by sin R. Okay, angle of incidence I, angle of refraction R. Mu Ga will be sin I divided by sin R. Now take the case if the light is starting from here. The initial case is when light is starting from here, this is your incident ray. Now light is starting from here. Here you have the incident ray and this is your refracted ray. In that case, this angle will become the angle of incidence and this angle will be the angle of refraction. For the convenience, we will be taking the same. Okay. In that case, the first medium is glass. Glass to air. When the light travels, you will be having the refractive index of air with respect to glass is equal to mu A divided by mu G. And that is equal to sin R divided by sin I. Refractive index of first medium. Here the first medium is this one and the second medium is this one. Okay. So sin of angle of incidence. In this case, angle of incidence is the refracted angle. Okay. Here we have the first medium. In first medium, the angle of incidence will be formed. And this is your second medium. In the second medium, you will be having the angle of refraction. Now we will be taking it as I. Okay. Now, when you multiply these two, this is your first equation and this is your second equation. When you multiply these two, what do we get? You will be getting mu Ga into mu Ag. For our convenience, we are taking the mediums as air and glass. If you are taking mediums as 2 and 1, refractive index of the second medium with respect to first medium into refractive index of first medium with respect to second medium will be equal to sin I divided by sin R into sin R divided by sin I. On cancelling, you will be getting that equal to 1, which means mu 2 1 will be 1 by mu 1 2. The refractive index of the first medium with respect to the second medium will be equal to 1 by the refractive index of the second medium with respect to first medium. This is the principle of reversibility. Clear? Next is the refraction of light through a rectangular glass block. Okay, here you have a rectangular glass block PQRS. The first medium is air. Then the light travels through glass and the third medium is again air. So first, here you have the incident ray. This incident ray, when it strikes this surface PQ, what happens? When you draw a normal, you will be getting angle of incidence. So here what is happening? The light is traveling from air to glass. Air to glass, which means a rarer medium to a denser medium. When light travels from a rarer medium to denser medium, we know that it bends towards the normal, right? The speed of light is decreasing in this case. Speed of light is decreasing and it bends towards the normal. You will be getting the angle of refraction with respect to the normal, okay? The angle between normal and the refracted ray. Now what happens is this refracted ray again falls on the opposite side. Okay, opposite surface it falls, that is SR, and then comes out to air. This is the second refraction. Two refraction is happening. First is from air to glass and the second is from glass to air. So when it travels from glass to air, what is happening in this case? The light is traveling from a denser medium to a rarer medium. Denser to rarer medium, the speed of light is increasing. When it comes from glass to air, the speed of light is increasing and it moves away from the normal. Okay. Now we have angle of incidence and angle of refraction in this case. Clear? Here, this ray is called emergent ray. This ray is called emergent ray. When you draw a line, a straight line, extending the incident ray, this is your straight line. When you extend the incident ray, this straight line will be parallel to the emergent ray. The ray which is coming out from the glass when it comes to the air is the emergent ray. Emergent ray and the incident ray extended will be parallel to each other. The angle between the emergent ray and the normal is called angle of emergence. So, 2 times refraction is happening in this case. When you take the case of a rectangular glass slab or a rectangular glass block. Okay, this is called when there is a shift happening, right? So, here bending towards the normal is happening and here bending away from the normal is happening. So, we will be getting a distance, a shift between the emergent ray and the incident ray extended. So, this shift is a perpendicular distance and this is called lateral displacement. Lateral displacement. Okay. So, first is from air to glass and the second is from glass to air. We have studied the principle of reversibility. Okay. Here we have 2 parallel surfaces. Then according to the principle of reversibility, air to glass, glass to air is how the light is travelling. Okay. First from air to glass and second from glass to air. So, principle of reversibility when used, you will be getting angle of incident equal to the angle of emergence. Okay. What was principle of reversibility? You had mu 21 is equal to 1 by mu 12. Okay. Here first medium is air, second is glass. In this refraction, glass is the first medium and the second is air. Okay. When you take this with the sign, when you consider the Snell's law, you will be having sine of angle of incidence and sine of angle of refraction. When you take the ratio and you will be getting angle of incidence is equal to angle of emergence. Here this angle and this angle are the same. These are the angle of refraction represented by R. Here this is the angle of incidence. Incidence for this ray of light and it is represented as R dash. These value will be same. Why? Because normals will be parallel to each other and here you have a transversal. Okay. So, this whole angle will be same. Then we are having this 90 degree and this part 90 degree. In that case, R and R dash will be equal. Clear? Angle of incidence and angle of emergence will be same. So, we have discussed what is lateral displacement. Here you have the incident ray when extended, you will be getting parallel to the emergent ray. Okay. Angle of incidence and angle of emergence are equal. This parallels. When you take the perpendicular distance between the emergent ray and the incident ray, you will be getting the lateral displacement. So, we will be saying that the emergent ray is laterally shifted from the original path of light. Lateral displacement can be defined as the perpendicular distance between incident ray and emergent ray. Okay. Now, what are the factors on which the lateral displacement depends on? The first factor is the thickness of block. So, when you are using a glass block, when the thickness of this glass block increases, you will be having the lateral displacement to be increased. Lateral displacement will also increase. Thickness and lateral displacement are directly proportional. When one point, that is when thickness increases, the lateral displacement will also increase. This is your first point. Now, the second one, the angle of incidence. Consider this case. Here you have angle of incidence. This is your angle of emergence. Here you have the lateral displacement. Now, take the case when you are increasing the angle of incidence. Here we are increasing the angle of incidence. This is your new incident ray and the angle of incidence has increased. Okay. Then it will undergo refraction. Somewhere here you will be getting, let's say, so this is your refracted ray. Okay. So, refraction angle will decrease in that case. And here you draw a normal. This is how you get the emergent ray. This is how you will be getting the emergent ray. Okay. Here you have the angle of emergence, new angle of emergence. Now, when this is extended, that is the incident ray is extended. Here you have a straight line. This is the straight line. We will be having the emergent ray and the incident ray parallel to each other, and the perpendicular distance between them will be giving you the lateral displacement. Here this is your lateral displacement. Now when you check this, you will find in the first case the lateral displacement is just this much. Here the lateral displacement has increased. So what happens? When the angle of incidence is increased, lateral displacement will also increase. Angle of incidence increases, lateral displacement will also increase. Okay, they are also directly proportional. Now the third is refractive index of the block. How does the lateral displacement depend on the refractive index of block? We know that the refractive index and wavelength are inversely proportional. Now when refractive index increases, the lateral displacement will also increase. What is happening when refractive index increases? The density is changing, right? So here when you have glass, so this is a new medium with a greater refractive index. The density has increased, bending towards the normal will increase. Yes, the refractive angle will decrease. It will bend towards the normal. Refractive angle will be decreasing. In that case, you will be getting somewhere here, you will be having the emergence. Emergent ray will be somewhere here. So the distance is also increasing. From the normal, this distance has increased, right? This is what is happening here. When density increases or refractive index increases, the lateral displacement will also increase. When we relate it to wavelength, when wavelength decreases, the lateral displacement will increase. Refractive index increases, lateral displacement increases. When wavelength decreases, the lateral displacement will increase. So when you consider VIBGYOR, violet light is having the least wavelength. Okay, violet light has least wavelength, therefore lateral displacement will be maximum when you are using violet light. Okay, now let us do problems. Here you have the first problem. Refractive index of water is 4/3. UW is equal to 4 divided by 3. We have to calculate the speed of light in water. VW. Speed of light in vacuum is given, which is equal to 3 into 10 raised to 8 meter per second. Okay. Refractive index in water will be equal to speed of light in vacuum divided by speed of light in water. From this we can write the speed of light in water is equal to speed of light in vacuum divided by refractive index of water. Put the values 3 into 10 raised to 8 meter per second divided by mu w is 4/3. 4/3. Taking the reciprocal, 3 into 10 raised to 8 into 3 divided by 4. 3 into 3 is 9, 9 divided by 4. 9/4 into 10 raised to 8, the unit is meter per second. 9/4 you will be getting a value 2.25 into 10 raised to 8 meter per second. Therefore, the velocity of light in water is equal to 2.25 into 10 raised to 8 meter per second. Okay. This is how you will be finding. Here you have the absolute refractive index because the first medium is air or vacuum. Now the second problem, orange light of wavelength 6600 angstrom travelling in air gets refracted in water if the speed of light in air is 3 into 10 raised to 8 meter per second and refractive index of water is 4/3. We have to find the first one, the frequency of light in air, second, the speed of light in water, and the third, the wavelength of light in water. Okay, given orange light of wavelength 6600 angstrom travelling in air. Lambda A is equal to 6600 angstrom, which is equal to, we know 1 angstrom is 10 raised to minus 10 meters. Therefore, 6600 into 10 raised to minus 10 meter. Meter is the standard unit. What else is given? If the speed of light in air is given, C is equal to 3 into 10 raised to 8 meter per second. And refractive index of water is given. Refractive index of water with respect to air is equal to 4 divided by 3. First question is to find the frequency of light in air. The frequency of light in air and the frequency of light in water will be the same because frequency is not changing. Frequency is a constant for a given source of light. Okay, we just need to find the frequency of light in air. We have the relation speed is equal to frequency into wavelength. From this we can write frequency is equal to velocity by wavelength. Here we have speed of light in air divided by wavelength of light in air. Put the values 3 into 10 raised to 8 divided by lambda A is equal to 6600 into 10 raised to minus 10. Okay, when you calculate this, you will be getting a value 4.54 into 10 raised to 14 and the unit of frequency is hertz. Okay, hertz is the unit of frequency. Now the second part, we need to find the speed of light in water. We have a relation. Refractive index of water with respect to air is equal to refractive index of water by refractive index of air, that is equal to velocity of light in air divided by velocity of light in water, which is equal to wavelength of light in air divided by wavelength of light in water. So this is a relation. If you remember this relation, you can find any value. Here we need to find the speed of light in water. We have to find the speed of light in water. So take the relation lambda WA. A is not necessary because here it is the absolute refractive index, is equal to VA is C divided by VW, which means VW is equal to C divided by mu W. Mu W is the refractive index of water. What is the value of C? 3 into 10 raised to 8 divided by 4 by 3. Okay, which is equal to 3 into 10 raised to 8, taking the reciprocal and multiplying, that is 3 divided by 4. 3 into 3, you will be getting 9 into 10 raised to 8 divided by 4. 9 into 10 raised to 8 by 4 will be equal to 2.25 into 10 raised to 8. And this is the velocity of light in water. Therefore, the unit is meter per second. Meter per second is the unit. Next part, we have to find the wavelength of light in water. Wavelength of light in water. How to find? Again, we'll be using the same relation. Mu W is equal to lambda A divided by lambda W, from which we will be having lambda W is equal to lambda A divided by mu W. Put the value lambda A, wavelength of light in air, is 6600 into 10 raised to minus 10 divided by mu W. Mu W will be equal to 4 by 3. 4 by 3, that is 6600 into 10 raised to minus 10 into 3 divided by 4. Okay, so on dividing, you should find the value. Will be equal to 19800 into 10 raised to minus 10 divided by 4. On dividing this, you will be getting 4950 into 10 raised to minus 10 meter. So 10 raised to minus 10, we know it is angstrom. Therefore, 4950 angstrom is your final answer. Clear? Problem 3. The speed of light in diamond is 1,25,000 km per second. What is its refractive index? We have to find the refractive index. Okay. Here, we know the speed of light in vacuum, which is 3 into 10 raised to 8 meter per second. And the speed of light in diamond is given, which is 1,25,000 kilometer per second. So, this kilometer per second should be first converted into meter per second. We know 1 kilometer is 1000 meters. Therefore, this becomes 125,000 into 1000 meter per second, or this can be written as 1.25 into 10 raised to 8 meter per second. Okay. Refractive index we have to find. Refractive index of diamond is refractive index of diamond with respect to air will be equal to velocity of light in air by velocity of light in diamond. Okay, VA by VD. VA will be equal to C by VD. Put the values. C is equal to 3 into 10 raised to 8 and VD is equal to 1.25 into 10 raised to 8. When you calculate this, 10 raised to 8, 10 raised to 8 can be cancelled. 3 divided by 1.25, you will be getting 2.4 as the answer. The refractive index is a ratio. Remember, there is no unit. 2.4 is your final answer. Next problem number 4. A ray of light of wavelength 5400 angstrom suffers refraction from air to glass. Taking the refractive index of glass with respect to air is equal to 3 by 2. Find the wavelength of light in glass. We have to find the wavelength of light in glass. What is given? The wavelength of light in air is given, which is equal to 5400 angstrom. Okay. What else is given? The refractive index of glass with respect to air is 3 by 2. Refractive index of glass with respect to air is 3 by 2. Okay. You will be having refractive index of glass with respect to air is equal to the wavelength of light in air divided by wavelength of light in glass. Okay. What we need to find is wavelength of light in glass, which is lambda G is equal to lambda A divided by mu GA. On crossing, you will be getting this one. What is lambda A? Lambda A is equal to 5400 divided by refractive index is given, which is 3 by 2. Taking the reciprocal and multiplying 5400 into 2 divided by 3. 5400 into 2 divided by 3. So, on cancelling, you will be getting 1800 here. 1800 into 2 is 3600 and the unit is angstrom. Here, you are not changing the unit to meters because here the quantity that we have is 1 refractive index. Refractive index has no unit, so it is not going to make any changes. Okay. When it is velocity, when velocity in meter is in meter per second, in that case, you will have to change this to meters. That's all for today. In today's class, we have discussed basic concepts about refraction and the refraction of a light ray through a rectangular glass slab. We have also solved a few problems. Hope you all enjoyed this session. I'll be back in the next session. Until then, stay tuned to Learno Hub. Learno Hub free hai par best hai. Thank you.